For nearly a century, cosmology has rested on a single elegant framework called we call it the Standard Model, a set of equations describing everything from the first fraction of a second after the Big Bang to the present day. It worked beautifully for decades, explaining observation after observation with extreme precision. But today, those equations are starting to fracture. Adam Riess, a Nobel Prize-winning physicist at Johns Hopkins University, has spent his career measuring how fast the cosmos is flying apart. He is reading his own data and telling us plainly that our model of reality does not add up. The trouble starts with a number called the Hubble constant. It measures the exact rate at which the universe is expanding right now, today, at this moment. You would think a single number like that would be easy to pin down. It has been a source of conflict since the 1920s. Edwin Hubble's original estimate made the universe look younger than the Earth. For decades afterward, astronomers split into two camps, fighting over whether the value was closer to 50 or 100. By the early 2000s, the number seemed to settle around 70. But as our instruments got sharper, a new split emerged. A stubborn gap formed between two independent measurement methods, threatening to erase a billion years of cosmic history and forcing us to reconsider the nature of the dark energy pushing everything apart. The Planck satellite mapped the cosmic microwave background, the faint afterglow left over from when the universe was just 380,000 years old. Physicists plugged those conditions into the Standard Model and ran the equations forward 14 billion years, resulting in an expansion of 67. The second method uses a cosmic distance ladder of supernovae to measure the present directly, finding a Hubble constant of 73. By comparing how bright these pulsating stars and supernovae actually are to how they appear from Earth, Riess's team confirmed this massive discrepancy. In a field where measurements are routinely precise to within 1%, a discrepancy of 8 or 9% is massive. It creates a billion-year gap in the age of the cosmos, shifting the size and expansion rate of the entire observable universe. If the universe expands faster than our model allows, the timeline for the formation of planets must shift. You're redrawing the history of everything. Scientists initially looked for errors. The leading theory was stellar crowding, the idea that the Hubble telescope's cameras were blending the light of nearby stars together, making target stars look brighter and closer than they actually were. To settle the argument, we launched the James Webb Space Telescope. Webb orbits 1 million miles away, using infrared cameras to cut through dust and separate individual stars, with a sensitivity that makes Hubble look like a pair of reading glasses. Many astronomers expected Webb's sharper vision to reveal the blending error, stretch the calculated distances, and bring the Hubble constant back down to 67, ending the crisis before the data even arrived. Instead, Webb confirmed the faster expansion rate of 73 with almost exact precision. In early 2024, the data showed that the distances held across thousands of stars. With measurement error eliminated, the field had to face the possibility that our understanding of the universe is incomplete. A separate team, led by Wendy Friedman, arrived at a different conclusion. Using independent star types, her team's analysis landed near 70, sitting in a no-man's land between the two major camps and adding a new layer of uncertainty. This disagreement suggests the distance ladder itself, the tool we've relied on for a century to map the nearby universe, may have unresolved issues at its foundation that no single telescope can fix.
Webb soon found galaxies in the early universe that were built faster than the Standard Model allows. These massive systems, existing just 600 million years after the Big Bang, rivaled the mass of our own Milky Way. This diagram shows the physics at play. To grow this large this quickly, these galaxies would need to convert every available atom of gas in their surrounding dark matter halos into stars. In a normal universe, that conversion rate sits around 10%. These galaxies appear to be running at 100% efficiency, leaving zero waste. Some of these were little red dots, galaxies where a central, ravenous black hole was devouring gas so violently it created an intense optical glare. From billions of light years away, that light makes a galaxy look 10 times more massive than it actually is. Even without those illusions, enough massive galaxies remain to challenge our current models. These ancient environments suggest that our understanding of how galaxies grow and evolve is either deeply incomplete or missing a fundamental piece of physics. Webb also observed young galaxies that appear strikingly stretched out, resembling cosmic cigars rather than the shapes predicted by our standard models. These prolate shapes suggest that dark matter particles might be lighter or behave differently than the cold dark matter scaffolding we've modeled for the past 25 years. Dark matter determines where galaxies form and how they cluster. If we have to change our assumptions about these particles, every prediction in cosmology, from gravitational lensing to the distribution of galaxy clusters, will shift along with it. One proposed solution is early dark energy. This theory suggests a hypothetical burst of expansion occurred in the first few 100,000 years after the Big Bang, giving the universe an unexpected kick before vanishing. This would shift the early universe predictions upward to match our modern measurements. There is also a second, quieter discrepancy called the S8 tension. It concerns how clumpy the universe is. When astronomers measure the clustering of matter directly, they find slightly less of it than the standard model predicts. These multiple tensions are likely symptoms of the same underlying failure in our physics. We are seeing cracks in the same wall from different angles. We have reached a point where our most precise measurements yield two conflicting, yet equally verified versions of reality. This is a direct conflict between the physics of the beginning and the physics of right now. The standard model still explains the cosmic microwave background and the abundance of early elements with extraordinary precision. No competing model has yet matched its track record. However, 95% of the universe, dark matter and dark energy, remains a placeholder name for forces we cannot identify or explain. The discovery of accelerating expansion in the 1990s resolved a similar contradiction by revealing dark energy, a force previously unimagined that brought the entire cosmic timeline into alignment. Current tensions likely point toward a similar, undiscovered property of spacetime. We are a species on a small rocky planet, using mirrors and math to argue about whether reality is expanding 6% faster than it should be. It is a magnificent effort. Our current map of the cosmos has hit its limit. The next version will need to account for these new anomalies, and it will likely reveal a reality stranger and more beautiful than anything we've previously imagined.